Designing a high-performance jet engine requires mapping every load and stress point along a single fixed coordinate system. This same logic applies to structural engineering on a construction site, where the load capacity of an I-beam is calculated by plotting the entire physical structure onto a standard X, Y, and Z axes. This approach assumes the steel is isotropic, meaning it will respond to a force along the Z-axis with the same resistance at any point along the beam. However, high-stress components often develop microscopic cracks and fatigue in localized areas that these macroscopic averages cannot predict. Relying solely on these global averages ignores the internal architecture of the metal, where the actual physical response to stress is determined. Under a microscope, that solid turbine blade is revealed as a polycrystalline structure, an assembly of millions of individual microscopic crystalline grains. This orange bounding box represents the macroscopic sample coordinate system used to design the entire component. Looking inside, each grain possesses its own orientation. The green arrows represent local crystal axes, tilted randomly relative to the macroscopic grid. This misalignment is critical because of anisotropy. In a crystal lattice, physical properties like stiffness change significantly depending on which local green axes you measure along. The mathematical challenge lies in translating these millions of chaotic, localized responses back into the single macroscopic reference frame of the engineer. Standard solid mechanics typically assumes anisotropy, where materials behave the same in all directions. Because individual grains are inherently directional, solving this translation requires a shift in our mathematical perspective. When calculating the movement of a machine part, mechanical engineers use a standard methodology for tracking objects through space. This is active rotation, as shown in the left panel. The coordinate grid stays fixed, and the physical object, the orange block, moves within that spatial frame. Material properties like elastic stiffness are tied directly to the atomic arrangement of the crystal. These properties do not physically spin or slide independently within the metal grain. Material science instead uses passive rotation. Here, the green vector representing the material property remains stationary, while the observer's coordinate axes rotate around it. We are mathematically adjusting our viewing angle to align our axes with the internal orientation of the fixed material property. Applying active rotation to internal tensors leads to significant predictive errors. To observe the material accurately, the shift to passive rotation is a mathematical necessity. We can demonstrate the effect of this perspective shift using a basic two-dimensional proof. We start with a green vector, v, which remains completely stationary relative to the original orange x and y axes. Next, we rotate our reference frame. The physical vector does not move, but we introduce a new dark green coordinate system offset by the angle theta. The dashed projection lines show that while the vector is unchanged, its numerical coordinates on our new axes have shifted. The same physical entity now has a different mathematical description. We calculate these new components using the transformation matrix at the bottom right, which uses the sine and cosine of our rotation angle to bridge the two frames. This 2D geometric rule provides the mathematical foundation for translating complex three-dimensional properties. For any model to be physically accurate, it must follow these geometric transformation rules whenever the coordinate frame rotates. Material properties are categorized by tensor rank, which describes their directional complexity. A rank 1 vector, representing a simple directional property, requires only one directional cosine term to translate into a new frame. Stress and strain are rank 2 tensors. Because they operate across multiple planes, they require 2 rotation terms to be calculated correctly. As the physical complexity of the property increases, the number of required rotation terms grows in direct proportion. The rank 4 tensor describes the elastic modulus, the property defining how a crystal grain resists deformation. To project the elasticity of a single local grain into the global frame, the calculation requires 4 distinct directional cosine terms, multiplied for every component of the tensor. The mathematical weight of our calculations scales exactly with the tensor's rank, ensuring the observer's perspective is mathematically rigorous. These tensor transformations form a practical engineering workflow that bridges the gap between individual grains and the final component. The calculation begins in the green panel on the left. We identify the material property as it exists within the local orientation of a single microscopic grain. In the processing phase, we apply the fourth-rank passive rotation formula to that localized data. The output, shown on the right, is the successful mathematical projection of that hidden local data into the engineer's global reference frame. This process transforms microscopic directional data into usable information for macroscopic design. A real engineering component requires executing this transformation across millions of unique grains simultaneously. Aggregating these projections allows us to predict the true bulk behavior of the entire physical component. This modeling capability is essential for manufacturing high-stress components that cannot be allowed to fail. Precisely calculating how millions of microscopic grains interact allows engineers to design materials that distribute immense loads without fracturing. Precision engineering depends on adjusting our mathematical perspective to accurately observe the material's internal response.